Alright, so today I'm going to be explaining this important paper with the title Graph Alignment Kernels Using Weisfeller and Leman Hierarchies. This AI stats paper in 2023. Graph kernels have become a standard approach for tackling the graph similarity and learning task at the same time. Most graph kernels proposed so far are instances of the R-convolution framework. These kernels decompose graphs into their substructures and sum over all pairs of these substructures. However, considerably less attention has been paid to other types of kernels. So we propose a new kernel between graphs, which reorders the adjacency matrix of each graph based on soft permutation matrices, and then compares these aligned adjacency matrices to each other using a linear kernel. To compute the permutation matrices, the kernel finds corresponding vertices in different graphs. Two vertices match with each other if the WL test of isomorphism assigns the same label to both of them. The proposed kernel is evaluated on several graph classification and graph regression datasets. So they present this WL graph alignment kernel, which is a new kernel between graphs. I think you are familiar with WL algorithm, so we skip this. So this is the contribution of this paper. What is WL graph alignment kernel? So a natural idea is to look for these permutation matrix P sub I for each graph G sub I of the data set. So we want to minimize this because different permutations we want to have, this is a good measure to minimize. Because so once we solve the above problem and compute these, we call them P1 to PM matrices, we can compute the following graph alignment kernel. And this is element-wise multiplication. The graph alignment kernel is positive semi-definite, and the problem defined in here, this problem aligns the graph adjacent matrices and imposes an ordering on their vertices. However, this problem has no polynomial time solution, so we next capitalize on the WL algorithm to impose an ordering on the vertices of each graph of the input collection of graphs. A naive approach would be to impose an arbitrary ordering on the color classes produced by the WL algorithm, and then sort the vertices of each graph based on that ordering. This would be equivalent to applying n by n permutation matrices to the input graphs, thus resulting into new adjacency matrices of dimension n by n. So, given a color sigma I, there exists at least one graph that contains the largest number of vertices. And we denote this by n sub sigma I. So n is the sum of the above number of all colors. Before comparing the adjacent matrices of the graphs to each other, they will be first transformed into n by n matrices. The elements of the jth column of D are this. So here they compute the kernel between the two graphs. So the WL graph alignment kernel with t iterations of the W algorithm is just defined here, because it's t iterations of the W algorithm. We take it into account to transform the adjacent matrices of the graphs. So this is they explain an efficient way of calculation of that. And this is the illustration of how the transform adjacent matrix is constructed based on the colors produced by the W. And they did some experiments on protein dataset and other benchmarks for graph classification.